So as a new example, let's try to evaluate a hard integral. And the integral I have in mind is this one here. So what I'm doing is I'm asking Mabel to compute the integral from 0 to 1 of the logarithm of t over t minus 1 minus t squared. And what you can see is that Mabel doesn't know how to do it, and the way that this is revealed is that Mabel will just reply with the answer. This is what Mabel does. Um, what I'm going to do is I'm going to vary the problem a little bit and look at what happens when you try other powers of the integrand. So I could put 1, for instance, and Mabel will give me a 0 out. I can put 3, and I get nothing. I can put 4, I get nothing. So what I'm going to do is to slightly more systematically, I'm going to see what these numbers look at. Apologize for the cat. So there's one thing I want to point out that so we saw that Mabel could give the integral 0 for the first power, and that in itself is not so impressive because it's fairly easy to see that the integrand is going to be odd through an axis of a half, which is halfway through the interval over which we're integrating. So the fact that I get a 0 out is not at all surprising, and actually it's a little bit disappointing that Mabel cannot see that the integral with the third power gives a 0. In fact, all the odd powers will give a 0 because of the oddness of the function here, so that the integral to the left of a half cancels out with the integral to the right of a half. So this apparently Mabel is not able to do, but we can certainly ask Mabel for an approximation. So I'm going to say from now on that the odd powers are uninteresting, they're all 0, but let's look at the even powers, and the first one, the one I'm most interested in, I can evaluate to, say, 50 digits very quickly, and I can ask Mabel if it knows this value, and indeed it does. It is pi square over 3. So how did it work? How did this work? Well, the point is that even though Mabel doesn't understand how to theoretically evaluate this integral, it certainly knows how to do an approximation by essentially taking a middle sum or something like that, probably slightly better than that. So getting a good approximation is not an issue, and we can see that if I give myself something like 50 digits, then I find a number that looks very promising. Indeed, this is as simple as pi square over 3. And I could do the same with the fourth power. That takes a little longer. I can identify it, and I get 7 over pi to the fourth power over 15. So what I'm going to do now is ask Mabel to keep on doing this for the first 10 values, and that's going to take a little while, and for some reason Mabel freezes completely. I cannot even stop this computation that I started, so I'm just going to have to wait for it, and I'll try to entertain you with some other things while we do this. So let's talk about an alternative to using identify, namely the so-called inverse symbolic calculator. So this is the inverse symbolic calculator, and I've already fed the first number that we found. So here it is, the one that starts 3 pi and 2, so on. We know that this is pi square over 3, but I can also put it into this inverse symbolic calculator, and it will give me a hit, which is slightly strange. It says that this value is pi square over the square root of 3, I assume, squared. So that's just pi square over 3, as we found before. This symbolic calculator, inverse symbolic calculator, is very old, and I'm using it because the better one that we mentioned in the book is down. So I mean, this has happened a lot with the inverse symbolic calculators. This, of course, is a very good idea, but somehow it never really there was never one place where people would put their effort into, as opposed to the online encyclopedia of integer sequences, which is sort of universally accepted as the place to go with your integer sequences for the inverse symbolic calculator, this has been moving around, and this apparently is the best one that is working at the moment. So the thing that I could then do, of course, is I could take my other constants. So I'm just going to check on my computation here. We're down to 8. I could take my other constants and try to feed them into the inverse symbolic calculator, and let me tell you what would happen. So if I do the same with the second constant that I found, I also get a hit. But already with the third one, which is this is one with 1419, I don't get a hit. So that in fact was not the case with the old one. So the old the better one that I'm mentioning, which unfortunately now is down, that would actually give me a hit. And let me look up what it was. It was 31 times pi to the 6th divided by 21. So you see what's happening here is that I'm not getting as much help as I had hoped, and indeed not as much help as when we wrote the book from inverse symbolic calculators. But definitely there's a certain pattern that's emerging here, that we're meeting pi with the same power as the power of the integrand. So this is a useful information that I'm going to start employing as soon as we've finished waiting for Maple computing L10. So I'll just be sitting here. There it was. Okay, so now I've computed these 10 values, and I asked Maple to identify them. I'm going to ask only for the first 5 because it takes Maple quite a lot of time to do identification when it can't do it. I mean, this is essentially the way Identify works, is that it tries a lot of different things, and one of the first things it will try is to look for some sort of relation that involves the important mathematical constants like pi. So that's why these values are found fairly quickly. But you see, Maple is not able to do it beyond the first 2 that we already found. So we're going to have to help Maple, and the way we're going to help Maple is to say, well, if we're indeed correct that what we're seeing here is a rational number times a relevant power of pi, then we can try to cancel the pi's and see if that helps. So what I'm going to do now is I will work under the assumption that the constants we are looking at are better understood if we think of them as something times pi to the same power as the integrand. So I will just divide through by that power, so that's pi to the 2 times n, and then I'll ask Maple to identify this. And so what you can see happens here is better. So I do get the same value, 31 over 21, that I used to get in the other symbolic calculator. I get something nice here as well. Then things are not so nice, and I get something here which I don't really think I believe. And we sort of see that this gets to be problematic. And in fact, there's an annoying behavior of Identify that I want to point out. So I let myself into this trap a little bit. So even though I was careful to compute 50 digits of these numbers that I'm trying to understand, and indeed you need this kind of precision in order to be able to work with Identify, then since the number of digits is placed at the default value, then you can see that Maple here works with 10 digits, which is default. So I'm going to have to ask Maple to work with 50 digits universally before I go on. So if I put digits now to 50 and I try this again, you can see that I get something slightly nicer. This is going to take longer. Actually, let's strike it down and do it like this. So I'm doing it in a for loop so that you have something to look at. And then you can see that Maple sort of gives up on the 9th value, and in a second it's going to give up on the 10th value as well. So that's the thing with this kind of um, analysis. It is pretty slow, so you're gonna have to sit and wait like you're doing now. Even though I have to admit this is probably not the best use of videos. Actually, let me see if I can strike it down. So, no, gonna have to wait for that. But you can see, I mean, definitely there's something promising in what we have found this far. Um, we found some fairly sensical fractions this way, I would say. Um, but as you can see, we're struggling a little bit with the last values here.